Hi everyone, welcome back to QNLP after a short break. We'll be hearing James Wootton on procedural generation using quantum computation. James.
Thank you. Thanks for the invitation to talk here. And it's nice to be back in my home county of Cambridgeshire, even if only virtually. So yes, I'm going to talk about procedural generation using quantum computation. And I'm James Wootton, and I work at IBM Quantum. So procedural content generation is the algorithmic generation of content. And this content could be a variety of different types of things, depending on what you need. It could be images or puzzles or levels in a game or maps in a game or objects or text as well. And it's typically used in things like games, but also computer graphics and art and other things. And there's many different kinds of algorithm that get used in procedural generation because there's lots of different types of content you can generate, and there's different reasons for generating it, different constraints it has to satisfy in order to be useful for whatever you're using it for. And for this audience, it's worth pointing out that some of these are grammar-based methods. So this isn't natural language processing. It's not strictly a subset of natural language processing, but there is significant overlaps. For one thing, because you might want to generate a language, the constraints that you have for it to be good content might involve some language processing, because you might want your text you generate to actually make sense, for example. And also the use of grammar-based methods means that lower down there's some overlaps as well. So yeah, and I think it'll be interesting and fruitful to look at some of the overlaps between procedural generation and natural language processing. However, admittedly, what I'm talking about today is some of the things I've done in procedural generation that do not overlap with natural language processing. And I think what everyone else is talking about today is probably natural language processing that doesn't overlap with procedural generation. But nevertheless, I think it's a step towards doing something interesting in the overlap. So I'm going to talk about some of the things that I've already done, and to put that in some context, it's good to have an idea of where quantum computation is at the moment. So at the moment, we're at a stage of it being very easy to run quantum software if you're targeting something like 20 qubits or less, because at that level, you can either run it on a simulator, which only requires your laptop, or you can run it on one of the devices that we at IBM put out publicly and for free, which go up to 15 qubits. On the other extreme, there are devices of many thousands of qubits. When we have them, we'll be able to build fault-tolerant quantum computers and to be able to do the textbook algorithms that have been developed over the last few decades. In that case, there are algorithms for things like optimization, constraint satisfiability, graph theoretic analysis, which will all be great for procedural generation. And so we know at that point, we'll be able to do things that are currently not possible, solve problems relevant to procedural generation that are currently not possible, and do things that are useful. However, at the level of sort of 20 qubits, we can't do anything that's unique to quantum computing because we can just simulate. But we can ask, can we do things that are nevertheless useful? Can we write circuits that are worth running, either on current devices or on simulators, and which give results that are useful for procedural generation? Because if we can, then the middle region, where the hardware is not yet good enough for fault-tolerant algorithms, but is nevertheless getting ever better and getting to a point where we can't reproduce it with supercomputers, well, we'll already have achieved usefulness, and so we can look for ever better ways to be useful and look towards the goal also of doing things that are unique for quantum computing. So what I want to tell you about now is a very basic method that I've done just to show that even with sort of 20 qubits, you can do something that is useful for procedural generation. It is worth writing quantum software, even if you're just going to simulate it. So what I wanted was an application targeted at a simulable number of qubits. And really, I wanted something like Perlin noise. So Perlin noise is an algorithm that is used extensively in procedural generation. People love it. I want that, but quantum. So this is mostly used for terrain generation. And so I wanted basically to come up with an interesting method for terrain generation. But it's also possible to do it in a much more rudimentary method using what is basically just a blur effect, like you'd have to blur images. So I started just with the notion of trying to do a blur effect. And the first step of this is to encode a height map, which you can also think of as a monochrome image, as the one you see up here. I'm hoping this Zoom widget isn't visible for you guys. So you want to encode something like a height map as a quantum circuit. And once you've done that, it's in the form of quantum software, so you can do quantum things with it. And basically, at a very basic level, modifying the circuit means modifying the height map. So you can just go and prod at this circuit and change things and see what changes. And the simplest thing I think you can do is just to add some single qubit operations to the end, which are rotations around the x or the z axis. And this will induce interference effects. Well, actually, if you do small angle rotations, this is a very small change to the circuit. And so you'll get small changes to your input, your encoded monochrome image. And the way that we have chosen this encoding is such that basically you get a bit of a blur effect. So here in figure A, you see 2 pixels. So we've got a very simple monochrome image of just 2 pixels. As we apply a little bit of this blur effect, it begins to blur these pixels. They bleed out into surrounding pixels. And if you apply that even more, you start getting something that can't really be explained by a blur, because it's inducing an interference effect. And it gets to the point at the end where if you apply a blur for a lot, you'll get quite a homogeneous image. But in this case, we get this chessboard pattern, and that's specifically because of interference effects. And in fact, I chose these 2 pixels not arbitrarily, but because I knew that this corresponded to a GHZ state, and I would exactly get this interference effect. So it's something that starts out as a blur, turns into an interference effect. It's basically a blur effect, but with quantum artifacts. And whether this is useful, it depends on whether you like the quantum artifacts, because if you don't, you should probably just use a standard Gaussian blur. Okay, so I use this, and I use this for terrain generation. So I have a process, which I'm not going to explain in detail here, but you can find all the code online, where I take a basic plan, as you can see in Fig C here, a basic plan for an island, and then I want to texture that island, make it less smooth, and make it have sort of realistic texture. So I take seed images, which are just some random pixels, I apply the quantum blur, and I really drive it into the interference phase to generate these textures. And these aren't just random pixel values, because you'll see that high points are near other high points, low points are near other low points. So there's some continuity in this. I call these quantum tartans. And then I splat these quantum tartans all over this basic plan for an island, and then you get a nicely textured island. So here's a 2D representation, and you can see a 3D representation also that I did in the voxel-based game engine. So it makes islands, which is exactly what I intended it for, but it also does other things. You can use it to encode other forms of data. So I encoded the 1-1 level of Super Mario Brothers. And as the level goes on, I turn up the quantum blur effect so that it becomes less and less what you might remember. Also, you can encode a couple of images. You can encode images, but you can encode pairs of images in multiple quantum registers, and then apply teleportation-like effects between those images, which results in getting teleportation-like animations. It's not great to do it on high-res images, which is why this image of J. Gambetta teleporting away is a little bit low-res, but it works quite well in some situations. I also did it with music, so it's something that can be used in multiple ways. But again, this is all me doing this using. So if we really want to see if it's useful, we would want to see other people use it. And this is something that we have seen. There is currently a game studio that is developing a commercial game, And in that commercial game, they are using this effect that I've developed for their procedural generation. There's also an artist, Libby Heaney, who's been using it in some of the art that she's been doing. And this is an example you see on screen from some art that she created as part of the quantum what they call it? The Qiskit camp that we had basically a year ago now. So it has been seen to be useful, not just to me, but also to external parties, which is a great test of something being useful. However, one thing to note is that the quantum origin has been an important selling point in each case so far, because in the game, they're making a sci-fi game. They want to build up a sci-fi aesthetic, and the quantum artifacts that come from this method are useful in that context. Libby, in her art, is looking at notions from quantum mechanics, so it's also useful in there as well. So in these cases, it's important that this method comes from the quantum region of algorithm space and isn't just sparkling linear algebra. We want the results really of a quantum algorithm to stand on their own and it not be important where they came from, but we haven't quite reached that yet. Okay, my fan is going crazy. That's probably being picked up on the mic. I will hope that moving on from that GIF lets it cool down a little bit. So sorry if you're hearing any noise from that. I'll now talk about another project that I have, which is looking at procedural generation, not just with a simulable number of qubits, but with larger devices. So what we're going to do when we have near-term devices. So what are near-term quantum computers? They are a collection of qubits that can be manipulated by single and 2 qubit gates. And these 2 qubit gates are constrained by the coupling map. So here you see a schematic of a device where qubit 0 is connected to qubits 1 and 5. So you can only do 2 qubit gates with those 2 qubits 1 and 5 if you want to involve qubit 0. The qubits are also described by a quantum state. You can think of this as a vector of 2 to the n variables. You can think of this as a density matrix with 4 to the n entries. I prefer to think of it in terms of the decomposition into Pauli, tensor products of Paulis, and therefore the variables are the expectation values of these Paulis. So what this basically means is that you describe everything in terms of the single qubit Paulis, which are the x, y, and z coordinates of the Bloch sphere for every qubit. And then you have the 2 qubit Paulis, which completely describe the correlations between pairs of qubits. And then we have 3 qubit Paulis, which describe 3 qubit correlations and 4 qubit and 5 qubit. And once you've described every multi-qubit type of correlation, you end up with 4 to the n numbers, which is quite a lot. However, you can argue that the single and 2 qubit Paulis are the ones that are most easily manipulated by the single and 2 qubit quantum gates. So what I wondered is, can we just focus on those? Can we just design an algorithm thinking simply about how the single qubit, so the coordinates of every qubit on the Bloch sphere and also the 2 qubit correlations between all pairs of qubits are manipulated, and not think explicitly about all of the higher order stuff that's going on. So what I wanted to do with this was make basically an AI for a civilization type game. So you have many nations, and each of those nations at each turn have to decide to do something. And I have a very simple model in which each nation chooses between 3 types of policy, either to be aggressive, defensive, or explorative. So I then map those 3 qualities to the 3 axes on the Bloch sphere. So the Z is how aggressive it is, X is how defensive it is, Y is how explorative it is. And so by where your state is on the Bloch sphere, you can see how much that nation is prioritizing these different types of policy. Similarly, between pairs of nations, we can have the correlations describe correlations between the nations. So you might have 2 nations that are very aggressive, but who are they going to attack specifically? Well, if you look at the ZZ correlations, then since Z encodes aggression, then that will encode how likely these 2 nations are to attack. So by reading out this tomography, by looking at the by running many times, taking statistics and looking at finding the X, Y, and Z coordinates of every qubit, and also looking at these correlations, you can deduce what's going on in the world and therefore what's going to happen. And then we embed this into a simulation of growing nations where the nations can actually take actions, they can grow, they can steal territory off of their neighbors, they can even steal city off of their neighbors. And then this, what happens in this feeds back into the quantum circuit, which is serving as the AI. So as a nation loses territory, then you will add single qubit gates, which will rotate it towards a defensive state. Or if one nation steals a city off another, then you will get to the point where their correlations will be manipulated by 2 qubit gates in order to fundamentally change the relationship between those two nations, which is what you would expect if one steals a city off another one. So in this way, every turn, we're running the whole circuit, which is encoding the state of these nations. We're looking at the state at the end to decide what happens. We take the actions, then we feed back the consequences into the circuit, run it again, and so on and so forth. This is all done based on something I call Quantum Graph, which is built on top of Qiskit. And it's basically just a layer on top of Qiskit in order to manipulate the circuits in the way that I want in this form. So that instead of saying I want to do this rotation by this angle, which is what you would usually do in Qiskit, it's you instead say I want this qubit to rotate more towards its plus state, for example. And with this, we have a procedure for generating maps. It creates geopolitical boundaries with a history behind them. At the end, you have nations, and you have their cities, and you have their borders, and you have a history behind all this. You know when each city was founded and why it was founded, and if it's changed hands and how it influenced the politics of its surrounding area. And so if you set then a game in this land, then there is a history behind it. It feels lived in rather than just something that was randomly created. There's games like Dwarf Fortress that use this kind of procedurally generated world and histories. And you find that a lot of people actually like looking at the histories and the world more than they do playing the game. So this is one kind of thing that people actually like in procedural generation. But we want to test how good this AI is. So you could just have the nations all behaving randomly all of the time. But instead, we want to see that they are actually behaving intelligently somehow. So we implemented it such that some of the nations do behave randomly, but some of the nations behave in the way that I've just described, where their state is changed based on what happens, and therefore they should be able to react to what is happening and do better because of it. And our metric of how well a nation behaves is how big its area is, because intelligent nations should expand more, you would expect, at least in this very simple simulation where expansion is what they want to do. You might think in real life maybe culture is better or other things, but in this world, expansion is everything. And if you run it on a simulator for 7, 9, and 11 nations, what you find is indeed the ones that have been implemented as I described do expand more. They are better implemented nations. The real test is whether this works on real hardware. So if we go to the 28 qubit Cambridge device and the 53 qubit Rochester device and run it, we still find that the nations that should be intelligent are doing better. So the device is able to implement this process and implement it in such a way that these nations are actually behaving in an intelligent way, at least in some rudimentary form. So yeah, through that, I have already got to my conclusions. So the conclusions are that even now, it is possible to make software, quantum software, that is useful for procedural generation. It is possible to write a function which creates a circuit, and running that circuit gives you some results that are useful. And we see this in the fact that some external parties are using it as part of their procedural generation in commercial products. if you want to learn more about these things, I've written 2 papers on procedural generation this year. You can see the archive links for them on the screen. They were both published in peer-reviewed proceedings for conferences relevant to procedural generation, which I thought was an important thing to do. It's been very nice this year to be able to present this work to the actual audience that are relevant at the end. And you can find all of the code that I used to do this on GitHub, and you can see the links for them as well. Things that we want to look into in the future are, when are we going to get to this point where we're not just doing things that are useful but could have been done by simulation, for example, on a normal computer, but when are we going to find something unique? When are we going to achieve quantum advantage? So that's something that we want to look into. And also, it would be great to look more into text generation and things relevant to natural language processing, because these are very interesting and useful. This is a very interesting and useful area of procedural generation. And I have the idea that maybe things like ZX calculus could be helpful in this, but that's something I need to look into more. Or you need to look into more if this has been a field that has interested you. Otherwise, yeah, that is all I had to say. So I'm happy to take questions, and I'll probably move off this slide because, again, the GIF is making my fan go crazy.
Thanks a lot for the inspiring talk and for the beautiful animations as well. So there's one question. Can you explain a bit more what you mean by quantum blur? Is it the same thing as a classical blur but faster, or is it a different kind of blur? So there was
yeah, so it's worse than the classical blur and it's slower, but but it has weird quantum thing. So yeah, basically I've encoded this such that each pixel corresponds to a bit string, but I've chosen the encoding such that the neighbors of each pixel have bit strings which differ on only 1 bit. So by making a small change to a bit string, you should like move some of that brightness to its neighbors. Now this is a problematic encoding because in terms of the Hamming graph, so of bit strings that are 1 bit flip away from other bit strings, there are more neighbors. This is an n-dimensional hypercube, and we have to squash this down in order to encode an image with it. So this is why you have things leaking into further away pixels. So you get some artifacts due to that encoding, but you also get some due to the interference effects. But it's designed to basically have the same sort of usefulness as a blur in a procedural generation, but be implemented in a quantum way. It's very slightly slower, and it has these artifacts. So it really does depend on whether the aesthetic that you get from the blur is something that is useful to you. It's encoded in a way that tries to get as many pixels into as few qubits as possible. So it doesn't allow a lot of high-level abstract control. But nevertheless, it can give effects that are visually pleasing, and in some elements of procedural generation, that is all you need. And so that's where you would target the usefulness of this.
Second question from Ross Duncan asking if you can comment on the difference between this quantum procedural generation and the previous work, the work on quantum GANs, the generative adversarial network.
Yeah, so well, procedural generation is a wide field, and things like quantum GANs could be useful for procedural generation. So in my own work, I've been targeting what I can run already with the resources that I have. As far as I know, quantum GANs, you can't do any more than just proof of principle runs at the moment, whereas I want to do things that are already useful. But yeah, as the technology progresses, things like that will become more interesting to look at because we'll be actually able to run them.
And then maybe a last question is, do you think, is there any test which might distinguish quantum PCG from the classical kind?
Well, I think it's probably, I don't think the end user will know, because really you don't want the end user to be thinking about the algorithm that has generated the content. You want to maintain the veil of mystery that this isn't some world that you have just come across in your game. But there are obviously in anything where optimization problems or things like constraint satisfiability problems are relevant, there are things that you just can't do at the moment. And so if once people realize that a computational method that otherwise couldn't be done must have been done to generate this content, then they will realize that quantum must have been behind it.
Thanks a lot. Well, thanks again for the talk, and then I think the questions keep on going on the Slack channel.
Okay, great. Thanks.
Thanks a lot.